as I go along summarizing RG, maybe there will be a good point to comment on this. All right. So today we're gonna continue our discussion of normalization group by discussing the Callan Symanzik equation. This is the equation that describes the running of couplings. There are various ways to view the Callan Symanzik equations. And what I present here is one of the simpler ways of thinking about it, which is very based on normalized perturbation theory, because you guys just learned this, right? And if later on in the course, once we get very comfortable with a few more, a more general setup, we'll do exact RG. Exact RG would be dealing with this problem. It would be a derivation of Callan Symanzik equation, which does not directly rely on renormalized perturbation theory. It's fully non-perturbative, and in spirit is closer to what we did in Wilsonian RG in the last lecture. So I'll go over that. So in the previous lecture, we started our discussion of normalization group, focusing on the principle of separation of scales, right? We said what the principle of separation of scales says. If I have a process, if I have a vertex, right, where there are a bunch of external legs, P1, P2, P3, P4 in Fourier space, and these are some low energy momenta, right? Some momenta that I'm dealing with around me. This correlation function should be independent of the details of the physics deep in the UV. The details of deep in the UV physics, right, that can run in the loops in all sorts of loop diagrams that I draw, will only contribute to changes in the couplings of my renormalized effective theory that I construct. What did I do? I construct for these operators. So once I renormalize the details, the physics at high energies is going to be irrelevant, right? So this correlator, the renormalized connected correlator or disconnected correlator, is independent of the cutoff. The cutoff, yeah, right? So I'll come back and comment on this again. This was the principle of separation scales, what allowed me or us to build buildings, even though we have not solved quantum gravity, right? Because there's an effective theory we construct at low energies that doesn't care about deep in the UV. Wilsonian renormalization group, we discussed it by explicitly putting in an explicit momentum cutoff into the partition function or generating function. So I'm just putting a minus sign here, treating it as statistical field theory, right? So this is a setup where my path integral over functions, I first weak rotate to frequency Euclidean momenta, and then I cut off the Euclidean momenta at some absolute value of k less than lambda, right? So if this is the k momenta, so for example, if you're in d dimensions, right, d space-time dimensions, you'll have to integrate over all momenta. So you have this d of k that we could think of as d of k and then the angular directions, right? So you could do that decomposition k. Sorry, there's k squared or whatever. You know what I mean. So here we're cutting off the radial direction, right? Which in Euclidean space is Euclidean momenta, right? K squared. All right, so that's the cutoff. The point is going to be that at the end of the day, our generating functional is going to be independent of lambda, right? In Wilsonian RG, what we do is next to the cutoff, we introduce another scale b lambda. B lambda, I sometimes call it M, capital M in this lecture. It's the physical scale, is what we call it a renormalization scale. So when we keep track of B, it's like keeping track of M over lambda, because we will see, we saw that under the two steps of our G, lambda comes back where it started. So lambda is unchanged. B changes, which is equivalent to M changes. So B is the dimensionless version of M. Good? So it's just, if you read Peskin, you'll see capital M. That's the same thing as B. All right. So now what does that mean in terms of the path integral? That's like the path integral d of phi of lambda could be split into the path integral with Euclidean momenta that are below the renormalization scale of interest, B lambda, and some modes that are precisely in that range. So these are the modes that are in between our cutoff and the scale that we just lowered a little bit further, right? Good. Then in this way, I can just, then I can think of my field as being the field below the low energy field plus these like heavy fields. So these are the light and heavy fields, this formalism, yeah.
So when we define the cutoff, you're saying that it's the magnitude of K, which should be below the lambda.
Yeah.
So that K is the Euclidean.
That's Euclidean K.
So, I mean, so like, is it always true that so like for example, the G naught component in here, so that corresponds to the Euclidean Hamiltonian variable.
The Euclidean Lagrangian, yeah. Right? Because we go to so if you remember when we were doing loop integrals, our loop integrals where we had to integrate over the Lorentzian fields, right? We first Wick rotated the Lorentzian momentum to Euclidean momenta, and then we saw divergences coming from large Euclidean lambda, L, K, whatever I call it, right? So that was, those were the divergences we identified, right? So here, I could talk quantum field theory, or I could just directly sit in Euclidean field theory where momenta are actually these. So the interpretation of K0 are thermal fluctuations.
Yeah, so what I was confused was that the generator of time translations in Euclidean, that need not necessarily be the generator of time translation.
There's, yeah, of course not. There's an I in there in between.
I mean, yeah, like for example, if you have the right Riemann mesh, then you have the boosts which are the generator of time translations in the Euclidean.
So if you have the Rindler space in the Euclidean picture, so and if you have the Rindler space, the the Hamiltonian in Lorentzian language is boost. If you go to Euclidean language, it becomes rotation in Euclidean plane.
Yeah, so like it's the boost in that plane, which is okay. I think I'm confused.
Okay, but ask it later if, yeah. Here you can view this whole thing as statistical field, right? All right, so we can split the partition function with the cutoff as the path integral with modes below the cutoff. Sorry, the new cutoff, right? The modes that are heavy, and then this is the shift in the Lagrangian, right? We just do the same thing that we did in the case that we had background fields, right? In step one, we explicitly perform the path integral over phi hat, the heavy fields, right? So that is like, we keep this part, we're not gonna touch this, we're gonna expand this, right? And explicitly perform the path integral d phi hat of these modes, right? So, yeah. Good. The result of this is going to be whatever it is. I'm going to take the log of it, put it up here. It's a functional of phi. I'm going to take the log of it, put it up here, and add it to Lagrangian as an effective term, as an interaction term that's been introduced because I've integrated out Euclidean momenta. Now, one consequence of this is that after doing this integral, your kinetic term changes, right? So here, basically under this flow, under this integration, any term that's allowed by symmetries will appear. So your S effective could be just systematic expanded as 1 plus del z m squared plus del m squared lambda del lambda blah blah blah, right? These terms, even though they were not initially in the Lagrangian, they could be produced on the RG flow. Good. Now the problem with step 1 is that now your Lagrangian is no longer, the fields are no longer canonically normalized. So the kinetic term is not canonical anymore, right? So to fix that, we do a rescaling by sending x prime equal xb, k prime equal k over b, and the field transforming this way, so that the kinetic term comes back to what it was. There's m prime, lambda prime, c prime, and d prime, right? Now you could say that under this transformation, b is less than 1, lambda has come back where it was. So under 2 steps of RG, the cutoff is unchanged, right? But b, or the renormalization scale, has come down. Or yeah, b has become smaller, right? So now this is the path integral you end up with, right? The cutoff is still the same, but this has changed. Now you have to keep track of b, right? That is the new scale in the problem. That's the renormalization scale that we're gonna keep track of. Now, it's clear by construction, I intentionally constructed 2 steps such that del mu phi squared, this term, is invariant under these 2 steps, right? This is the second step was engineered such that this term comes back where it was, right? So if I start with a Lagrangian that has no m prime, lambda prime, c prime, d prime, all of those are 0, that's going to be a fixed point of renormalization group. What do I mean by fixed point of renormalization group? View the value of all these couplings as the space of all couplings is a parameter, is a theory space. I have a space of all possible quantum field theories. I can write down for a scalar field theory, right? Then these renormalization group flows are flows in these insanely infinite dimensional spaces. These flows have fixed points. A particular fixed point is the trivial theory. These are called trivial theories. Half del mu phi squared is a trivial theory, right? I'm going to comment on that a little bit more. Any questions about the 2 steps? So when b is almost 1, which means that it's a thin momentum shell I'm integrating and then scaling back in, these transformations become continuous. These are called the RG flows equations. So here's phi of p1 all the way to pn. With a cutoff lambda, an action L should become phi prime, or Lagrangian L should become phi prime of p prime, this lambda effective B, right? This is the fully non-perturbative feature. We said that if I can ignore these delta terms, right? If I can ignore these terms, which were coming from actually loops, right? What I end up with is this simple picture where G prime is GB to a power of delta, right? Because I can just literally solve these equations. And then that split, that is just basic dimension counting that splits my operators into positive deltas, right? Irrelevant, negative deltas relevant, and delta equals 0 marginal. So the relevant deformations grow in the infrared, right? There are very few. The thing that you need to know is this: there are very, very few relevant terms, and that's the magic of field theory, quantum field theory. The vast majority of almost all of them, actually, because they're infinite. The space is infinite dimensional. In this space, infinite dimensional theory space, most directions are unstable. You just flow back as you go to infrared, right? It's only a finite dimensional subspace of this lower dimensional, this infinite dimensional theory space where you actually flow, your theories flow on, right? These are sort of stable subspace and they're finite dimensional. And those are the theories that we should care about. Those are the renormalizable theories. So comments, a set of comments I want to make. Wilsonian renormalization group is always, or in general, renormalization group is always from the UV to the infrared. If you have the UV data, you could integrate it out. But if you have integrated out, you cannot put it back in because you've lost that information. So there is some inherent irreversibility in normalization. It erases some UV details, right? After you flow in the IR, towards the IR, the RG flow is designed such that the low point, the correlation function of light operators is unchanged. But of course, you're losing the information of the UV correlators, but you don't care because they don't exist and you don't care about those, right? I can build buildings, but if I want to ask a question about some correlation functions of some physics of buildings that with a precision that involves like M Planck, I'll have to do something better than FECOLMA, right? My FECOLMA has already integrated out that physics. I have no access to it. So Wilsonian RG flow flows from UV to the IR. There is a lambda cutoff. Importantly, as we just discussed, lambda is unimportant, right? The only thing that your theory depends on is the renormalization scale, right? Lambda doesn't matter. For you pick the lambda, I don't care. I can always renormalize it, and the final result is independent of lambda because the counter terms just get rid of it, right? At the cost of local action, local terms. If under the RG flow, I was generating non-local terms, that would have violated locality principle, right? So it's very nice that separation of scales keeps me in the space of local quantum field theories. So here, my phi and g's, phi is the field, right? Become function of renormalization scale or B, right? B lambda. And the theory will be a function of that in general. So if I have in the renormalized theory, if I have phi r of x1 to r xn, it's independent of lambda, but it depends on B. I said that. B is m over lambda. This is cutoff. This is renormalization scale. Just wanted to make that very, very clear. Good. I said this because we have integrated things. RG is irreversible. That's an intuition, okay? That's an intuition that in some cases will turn into some deep non-perturbative results in quantum field theory called C theorems, but yeah. Deep in the infrared is only sensible to include renormalizable terms in the Lagrangian. Is this clear? Is this principle clear? Why? Because if you had non-renormalizable terms, they would decay as you go to further in the infrared, right? The only way that you will have to include non-renormalizable terms in your Lagrangian, infrared Lagrangian, is that for some reason, the coefficient of that term in the UV was just enormous. It was insanely large because it decays exponentially, right? Which means that there's a nearby scale where there was new physics that you've missed. Fixed points of a normalization group are scale invariant theories. There's a simple example we've dealt with in this course is minus half del mu phi squared. This is a scale invariant theory, but it's not the only case. Now, near a fixed point, for example, the trivial fixed point, free scale invariant theories, I can deform the theory, right, by del some I g I o I, right? This is my new Lagrangian. And here, the terms that I can add are those that have dimensions less than d, right? These are the relevant operators. All the other terms are irrelevant. So if I start, what can I put here? I can put phi squared. Phi squared term is relevant in all dimensions. Why? Because the dimension of phi squared is d minus 2, and it's always less than d, right? So no matter in what dimension you are, mass term always grows in the infrared. Unless there's a symmetry that forbids the mass term, you should always include mass terms for your fields. Always in arbitrary dimensions. Scalar field theory. What is the symmetry that forbids mass terms? We've seen that in the previous part of the course. Gauge invariance. Yeah. Del phi squared What's the dimension of that? The dimension of that is marginal, D. That's always marginal, right? But that's okay, because that's actually the term we start with. So of course, that is marginal. Phi n has dimension n d minus 2 over 2, and in low enough dimensions might or might not be relevant. But it's pretty clear as we go to higher n, you quickly become irrelevant. So I don't need to consider any higher n's. Del phi to the power of n is even worse, right? So they become increasingly irrelevant. This is basically the two things that I can universally say. Now let's discuss, as an example of this principle, scalar field theory in dimensions larger than 4 space-time, 4 dimensions and lower. Okay? To see the power of normalization group flow. So I'm going to talk about the space of all couplings, theory space. So it's an infinite dimensional space. There is the m direction, mass direction. Lambda 4 is a phi 4 term. Lambda 6, lambda n. There's a coefficient for every term operator in the Lagrangian I can put. If I have to make it more orthogonal, blah, blah, blah. But it's an infinite dimensional space. Right? And we've said this before, in a normalization group, you just move generically in an arbitrary direction. Not arbitrary direction, but you move generically. However, the point is that so there will be fixed points. Fixed points are points here, like there will be points in the space of all couplings, where there is a theory that says that under RG flow doesn't move, just sits there. Right? Now, you take this theory, these are seeds for building quantum field theories. You take one of these theories, you deform it by a tiny bit, which is like in the theory space, you consider a theory very close by. Now, like for example, in the scalar field case, and D larger than 4, let's turn on this phi squared term. That's a relevant deformation. This is the mass term. And this grows under RG. So under RG, this becomes larger. So the flow will push this point that way to larger values. In larger than 4 dimensions, lambda phi 4 and all the other couplings, higher order couplings, they're all irrelevant. So no matter where you start in the infrared, you just flow towards this fixed point. Actually, not fixed point, but you flow and m becomes larger. Right? There is basically an infinite dimensional space. There's this crazy flow. But if you start with if you start with like a finite dimensional subspace, you're not guaranteed to stay on that finite dimensional subspace, as I said, right? But if you start with this one dimensional thing of m squared, everything flows in that direction. So from the point of view of an observer sitting in the infrared in higher than 4 dimensional space, all that you need to care about is massive free fields. Scalar field theory in 4 dimensions and higher is trivial. It's just scalar free fields. It's just free field, massive free fields, and it's Gaussian, it's integrable, there are no interactions. Another way of saying is that there exists no interacting scalar field theories in higher than 4 dimensions. If you hear this expression, this is what it means. Of course, as an effective field theory can exist, right? But it requires some fine-tuning. Is that clear? Now let's consider the D equal 4 term case, which is the case of interest for us. So the relevant term is m squared phi squared. Then there's a marginal term, lambda phi 4. And let's just for now assume that there's a Z2 symmetry that forbids phi 3. All right, so here are the equations for the RG flow, right? This term is marginal, but marginal based on the analysis of just dimension counting. The dimension counting ignored this del Z and del m squared and del lambda, right? To decide whether it grows in the infrared or decays in the infrared or remains exactly marginal, you have to do this in the presence of these, you have to do this calculation in the presence of these corrections coming from loops, right? So we need to compute del lambda. We did that actually, right, in the previous lecture. And lambda prime, after we integrated this shell, became lambda minus 3 lambda squared over 16 pi squared log of 1 over b. This was actually attributed to this diagram calculated. This means that it decreases slowly. So we call these operators marginally irrelevant. What does it mean? It means that here's m, here's lambda 4, lambda 6. We still end up with the same picture, but in all directions, things like decay really, really fast, like point directly towards the fixed point. But the lambda 4 coefficient decays a lot slower, right? Because it decays at like a slower, well, it's marginally relevant. So these are the flow pictures you would draw. We would still find the same result. Deep in the infrared, there are no interacting scalar field theories in 4 dimensions. So if you hear this, that's what, if you hear this statement that there are no interacting scalar field theories in 4 dimensions and above, that's what it means.
What is the particle error hits indicated over there?
What is what?
The particle error hits in the diagram. Fine.
So these, what is?
Yeah, the blue ones are okay. I don't understand. What are the particle error hits, like the particle directions?
These directions.
Yes.
These are the direction of coupling. So it's the space of
What is the
coupling.
coupling rate?
Yeah. So lambda 4 is a 5-4 coupling. Lambda 6, let's say, is 5-6. There will be couplings associated with del phi, blah blah blah. Right. These are all sorts of different couplings, space of couplings. Because naively, like what is nice is that naively you would have thought that every point in this space of couplings is a theory. But RG flow tells you that no, that's not true. These theories are related. But because of the fact that RG is irreversible, there's a direction to the flow. There's a sense in which that the space of all quantum field theories is not just like it's like a map with topography. There are points that are higher. There's a Mount Everest. There are theories that are lower, right? And they're related because one of the higher one can flow to the lower one, but not the other way around, right? So there is like a height function defined on this space, if you wish. Is that clear? All right, good. So this was the equation that we had. And then when b is near 1, you could write this equation as b del b lambda of b is 3 lambda squared over 16 pi squared. Remember that this relied on the assumption of small coupling, right? Because there are corrections to this at higher loops that are higher orders of lambda. So this equation is highly nonlinear. If lambda is small, I can write this down. So this already also assumes that lambda is small. You have to be within the perturbative regime. So these equations are really valid in the vicinity of the fixed point. Away from the fixed point, I'll tell you there is, in general, some functions that sit there that are functions of lambda, right? And that's going to be the story of non-perturbative RG. Because under RG, lambda is kept fixed and b is changing, that's like m is changing, and b del b is mdm. So if you see sometimes people write this in terms of mdm, that's what it means. No, that is actually, so b is dimensionless, right? And that is why we write MDM, because M is dimensional 4. Want to make sure that we're talking about running of dimensionless stuff, right? Our equations, we want to write them in the language of dimensionless stuff. What sits on the right-hand side of M del M of lambda is a function of lambda that captures the dependence of lambda on scale. That's called beta function for the coupling lambda. That's the name, right? So beta function, of course, in normal perturbation theory will admit some expansion in lambda. There will be higher loops corrections, higher order corrections, right? And I said this, there are no interacting scalar field theories in dimensional structure. Any questions? Now let's consider scalar field theory in less than 4 dimensions. Lambda phi 4 is relevant, and the theory flows away from the fixed point. So there is room for theories, interacting theories in the infrared that are more exciting than just massive free fields. So there could be, and where does it flow? What's the end point of our G flow? Any thoughts actually? What could be the end points of our G flow? Sorry? One possibility is fixed points, which means a genuinely interacting conformal invariant theory, which is not del phi squared, del mu phi squared. So those are conformal field theories. If the theory is relativistic, if the scale invariant, we argued that is perhaps conformal invariant. So those are conformal field theories. What are they? Can I describe them using Lagrangians? Are there non-Lagrangian descriptions of them? These are questions that one should ask. Another very interesting comment, I invite you guys to think about this, is that consider a theory, quantum field theory, in 6 dimensions and above. Sorry, yeah, 6 dimensions and above. There are no terms in the Lagrangian you can write down that would be relevant. So in higher than 6, this is usually in 6 dimensions, the belief is it's a long story. Now I'm going on a tangent, but the belief is that conformal field theories are isolated points. This picture of RG flows no longer exists. And in higher than 6 points, good luck. There's really all you have is just free field theory. That's all you've got, massive free fields. And the issue is really counting relevant operators, right? All right, so let's come back to lambda phi 4 in lower than 4 dimensions. Lambda grows, oh, actually, for a second, because now I have 2 directions that grow, m and lambda. For simplicity, I have to solve the equation simultaneously to simplify my life. Let's say the mass squared is absent. Mass term is absent because of symmetry, for example, right? Let's just simplify my life for now. So this is how lambda prime will evolve. We saw this, or we've seen this at some point in the previous lectures, right? As d goes to 4, of course, you have to recover the result that we had before. Beta function was 3 lambda squared, 16 pi squared. This was a marginally irrelevant case. But in d4 minus epsilon, beta function will be 3 lambda squared over 16 pi squared minus epsilon, something linear in lambda. I'm being a little bit ambiguous about what epsilon is. It could be 1, could be 2, it could be some formal thing, some non-integer. But now, because this term is positive, what are fixed points of our G? They are zeros of the beta function. This is positive, and that is why in 4 dimensions, the only solution for this is lambda equals 0. Right? So massive trivial theory. But now that I'm in d minus epsilon dimension, there is a linear term, and these two with a minus sign, they can cancel. So there will exist, depending on the theory, some lambda c critical lambda where beta function becomes 0. This is a new fixed point. But notice that I can tune these. I mean, of course, these equations are valid only for small lambda. But I can tune my renormalization group flow such that this new fixed point is reachable within perturbation theory. In principle, it could have been whack, right? But here's a setup. It's a very famous setup that we arranged. So we'll probably comment on this. This is room for like whole lecture on this, but this is one of the very, very few instances where you could flow from 2 fixed points using perturbation theory. So if you're interested, read up on Wilson-Fisher fixed points. So there's a competition between this term and this term, right? If I'm to draw the theory space, so here's the fixed point. M squared is the relevant deformation, so the flow is in that direction. There's flow in this direction. Here is more complicated. That's why I was ignoring fine-tuning M equals 0, right? So this flows away until it reaches a new fixed point, lambda c. 1 second. These directions are flowing here, but above this, actually, if you do the analysis a little bit more carefully, you see that this is a fixed point. So these guys actually flow this way, but then there's a mass direction that can grow this way. Yeah.
Two questions. Number one, are these fixed points repulsive, attractive, what?
Well, depends on the direction. This is repulsive, this is attractive.
Okay, so it's like.
Yeah.
Okay, gotcha. Second, can you have a complicated behavior like limit cycles and stuff like that?
Can you have a limit cycle? If you have a limit cycle, it would violate one of the bedtime stories I told earlier. The irreversibility of RG flow. Right? The picture that I was depicting that like there's height and RG flows, it flow down. It means that like, yeah, you can't go back up. So there should be no limit cycles. Now, is that a formal proof? In some lower dimensional theories like 2D, we could prove that. In 3 dimensions, there's almost a proof. In 4 dimensions, there's almost a proof. Higher dimensions, it's up in the air. All you need to say is up to 6, right? You don't. 2 dimension, there is Zamolodchikov C theorem proof, which is like rock solid. And it's very sharp. You can prove it just using relativity.
And it tells us that it's the only possible limiting condition, limiting behavior for RG flows of fixed points.
Well, what a C theorem is, it's a function that's you define for every quantum field theory that you prove is monotonically non-increasing under normalization group flow. That will tell you that cannot exist any. And that actually it has to be stationary as well, which means that its derivative is 0 if and only if you are at the fixed point. Or like you could be on a fixed surface, right? Because imagine a scale invariant theory, conformal field theory. If an operator is exactly marginal, that will deform your theory on a conformal on a fixed surface manifold, right? There are examples of that, n equal 4 super angles. All right, but in general, there can be strongly coupled fixed points in the infrared, right? Because in lower dimensions, we just argued that these things can grow, right? And how are we going to go about describing them? We just said that perturbation theory just fails, right? So how are we need a non-perturbative description of quantum field theory. We desperately need them. Because in the infrared, it's natural to land on these not strongly interacting theories. We don't know how to write down the Lagrangian for them. We can't even in principle calculate things easily. That's why it becomes important to classify and understand conformal field theories in lower dimensions. Because if you understand one of these conformal field theories non-perturbatively, then you could do what I call conformal perturbation theory, right? You could take one of them, just deform it a little bit and do a QFT around that. In D equal 2, if you remember, phi n terms are all marginal, right? At least superficially. And there's been a lot of progress in understanding and classifying 2D CFT. So that's a semi-success story. Any questions? I'm running really behind.
Like speed doing.
Can you
have a flow which doesn't end?
what are the possible endpoints of your normalization group? One is fixed points. What other options are there? There are 2 other options that one can imagine. What's the other one? Sorry.
Lambda's coupling.
Sorry?
Lambda's the coupling constants of the interaction terms.
Yeah. So,
So,
so let me just tell you about other possibilities. The theory can have a gap, right? Which means that you integrate momentum modes, but there is a mode, there's a minimum energy excitations. There's the vacuum of the theory, and then there's excitation that's above it and requires a minimum mass m squared, right? If the theory has a gap, you integrate the theory all the way to the gap. Beyond that, there's nothing to integrate out. That's one possibility. Gap theories. Remember that CFTs are gapless. I don't know if that's familiar or not, but there's no gap in CFT. There's a third option. A third option is a famous case. What's a theory that is not a CFT, but it has massless modes? Spontaneous symmetry breaking, right? Spontaneous symmetry breaking is another option. So this is when you end up with Navier-Stokes bosons. All right, that was perhaps too quick. Let's get back to the. All right, any other questions? I have to start Callan Symanzik. I haven't said a word about it yet.
just a bit irrelevant one which is the massless modes which arise from spontaneous symmetry breaking. For example, can we account for the Kaluza-Klein modes from this?
Kaluza-Klein one. So we're not doing dimensional reduction, right? So it's just like we take.
So also from this Kaluza-Klein tower, then there is a massless at the moment.
Yeah, let's not get into intricacies of those cases. All right. Any other questions? Now I want to switch gears and talk about Callan-Symanzik equations. Callan-Symanzik equations are precisely the RG flow written for connected correlation functions. But I'm gonna motivate it using renormalized perturbations here, as I said, but yeah, it's just like putting all of this in a more coherent form. So if you recall renormalized perturbation theory, for example, in lambda phi 4 theory, take it to be massless for simplicity. We only need to worry about one operator, lambda phi 4, right? We want to renormalize this in renormalized perturbation theory. What do? We took the bare Lagrangian, we wrote it as a renormalized Lagrangian, we introduced the Z's, right? Renormalized Lagrangian plus counter terms, and then we introduced normalization conditions. So these are the normalization conditions for the 2-point function at some renormalization scale m squared. Good. And then this is a normalization condition for the 4-point function at scale m squared. Remember that these are just like center mass. S was center mass, right? Okay, and this m is precisely the normalization scale we've been talking about, that b. So phi of r is z of half of m. It will depend on m of phi naught, and lambda will depend on m. Not the cutoff, right? All right, so how does this go? This is another way of viewing beta functions. I'm going to give you a different way of viewing beta functions. It's of course intimately related, and at some point in the course we're going to relate them. Maybe you can see it already. Take the endpoint function of the bare fields with bare couplings, right? This, sorry, this could be viewed as, because if you recall this calculation, I can do this calculation using the bare fields, or I can do it in renormalized perturbation theory in terms of a theory with lambda m, with all sorts of counter terms and stuff, right? And then there is z of m. The left-hand side is independent of renormalization scale, right? So the infinities in this correlator were canceled out by the counter terms, right? This is the endpoint function. I'm going to take it to be connected to simplify my life. MDM of z to the power of n over 2, right? N over 2 because there are n of such entries of Gn of lambda m and m is 0. Right? That's just this left side does not depend on m. All right, so let's take derivatives. MDM could act on z half, there are n of m, and comes out. MDM can act on lambda m, right? And MDM could come from this dependence on m. This is the equation we end up with. This is called the Callan-Symanzik equation. MDM of lambda is beta functions. We said that before. MDM of z half is gamma of lambda. This is wave function normalizations or operator normalizations, right? Remember, notice that this equation does not care about xi's. And lambda. So the Callan-Symanzik equation is this. The connected correlator is here, right? MDM beta lambda plus n lambda of Gn is equal to 0.
With defining the pair theory at the UV experimental study.
Yes, except that because there are infinities, this analysis is super formal. Right? So the Baire theory has all sorts of divergences. Or sorry. Yeah, the Baire theory has all sorts of divergences that I eat out in counter terms so that the renormalized correlation functions are finite, right? To eat out the divergences of this, I do and the counter terms come with or on the left hand side there's no m. On the right hand side, in splitting into renormalized versus counter terms, I've introduced an arbitrary parameter m. And the renormalization scale is that m, right? That splits the two. I have made sure, due to renormalization, that these counter terms capture all the divergences here, and this phi r's are divergence free. Right? Now, if I want to consider how this left hand side, so left hand side is independent of m. If I want to see how, if I act with derivatives on m, all the m dependence comes from the counter terms. Right? And that is capturing the physics of running of the endpoint function, of normalized endpoint functions with that. Right? Because however the renormalized endpoint functions run, the running should be canceled by counter terms. So they have the same behavior. Because the left-hand side is independent. This is a Callan-Symanzik equation. So it would be helpful to work out a bunch of examples. So let's compute beta lambda and gamma lambda in renormalized perturbation theory for massless scalars. I say massless because I don't want to have two directions that mix up, right? So here's the 4-point function, the connected 4-point function. There is a lambda phi 4 term. There are the STU channels for this loop. There's a counter term. There's lambda q terms, blah, blah, blah. Right? This is up to order lambda squared. So my Callan-Symanzik is MDM plus beta lambda del m plus 4 gamma lambda 4 because it's a 4-point function, right? G4 of P1 to P4. This has to be equal to 0. So let's calculate G4 of P1 to P4 up to one loop or up to lambda squared. So this diagram is minus I lambda. This diagram we calculated minus I lambda squared I v of s, if you remember. So this was v of s. We notice that I'm in the massless regime, so I just put equals 0, right? And then there's a t channel, there's a u channel, you sum them, and then there's a counter, right? And then here are the external legs. All right, very good. So first, notice that if I want to renormalize my G4 at scale M, it means that this term should cancel when S is equal to T equal to U equal to M squared, right? So this case would be 3I V of M squared, right? Minus I lambda squared here, should cancel with minus I del lambda. This is this normalization condition. Let's make sure that step is absolutely clear, right? So this is the normalization condition, means that this term should cancel at scale M squared. Scale means S equal T equal to U equal M squared, right? That's my condition. So this clearly tells you that your delta lambda, your counter term depends on M. We evaluated this counter term using Feynman tricks and all, and this was the answer. In the D going to in for limit, there was 3 lambda squared over 4 pi squared, 1 over D minus T over 2. This is that epsilon term in the dim reg, right? And then there's minus log of M squared. That's the most important part. And the rest is independent of M. We only care about the M dependent of M, part of counter terms. All right, so we have to take derivatives, right? So this is the G4. The only M dependence come from delta of lambda, right? We take derivatives and this is what we get. Del M of G4 is 3 lambda squared over 16 pi squared, right? That tells me what the beta functions are. So this was the result that we saw earlier, right? We saw this by integrating a tiny momentum shell, thin momentum shell, right? In Euclidean and Wilsonian RG. But it's the same answer, same result. If I'd actually kept 4 minus epsilon dimensions, I would have found the term that is like linear and then they cancel. They don't get that.
Wait, so you mentioned that was one method, this is a different method, so are they
They're equivalent. I just presented them differently. They're equivalent. I did not go in between the two. It's not hard to do. I just have to go in between the two. I'll have to define what a wild transformation is. It's the symmetry of the partition function, blah, blah, blah. I have to say all of that. I'm trying to avoid that. They're equivalent. Any other questions? Now consider the Callan-Symanzik equation for the 2-point function. So this is what the Callan-Symanzik for 2-point function is. Now, if you recall from our calculation, at one loop, there are no propagator corrections. There are no corrections to propagate at one loop. So there is no dependence on M or lambda at one loop. These are the diagrams, by the way. So this is it. There's a counter term. This is the one loop. And the correction is order lambda squared. What does that tell you about beta lambda? What order would beta lambda be? This equation will have to give you 0. This guy starts at order lambda squared. So beta lambda has to be order. This is order lambda squared. If I act on this with M del M, what order is it? Still lambda squared. That has to cancel with beta lambda del lambda. Lambda cubed. Think about that. All right. In a general theory, the M dependence, beta and gammas, are calculated using the field strength and vertex counterterms. So if you wish, when we did renormalized perturbation theory, the thing that we get out of it is we're gonna take these counterterms, take derivatives instantly with respect to M squared, right? To get the beta function, and that's all I need to know. Because I will renormalize my theory, and I know how my theory changes as a function of my renormalization scale. So for any the 2-point function, for any massless scalar field theory, we'll have this propagator, loop diagrams, and counter term. This is I over P squared. This loop diagrams will basically look like I over P squared, a log of lambda squared over P squared plus finite. Why? You guys remember why this was a form? Any thoughts? What is the first loop diagram? That's the first correction. It will look like this. Oh, sorry. This is the first order. No, not to this. Sorry. No, it's actually this. And then there will be these. Then there will be these guys. We already calculated. Just go and look at them. It's just a counting of it's just a counting, operator counting, dimension counting that will give you the answer. And then the counter term is of course I over P squared over P squared, I P squared del Z. Right? The only M dependence comes from here. To get the divergences to cancel, you will have to have this term cancel this bit. Right? Which tells you that del Z has to be A log lambda squared over M squared. A is just some function, calculate, right? Plus finite piece. As I said, beta lambda is higher order in lambda, so we could drop it. And to the lowest order, the Callan Symanzik equation you get is this. Minus I over P squared M del M of del Z plus 2 gamma I P squared is 0, which means that gamma is minus A. So you can directly read off gamma every time you have a theory that simple. I'm going to give you an example that you have already seen. I'm going to tell you why this is useful as a cheat trick. Consider QED. Renormalized perturbation theory for QED at one loop, right? The diagrams we have, I'm just going to focus on counter terms. You remember the rest, right? So there was the delta 3 counter term that had to with the counter term of the propagator for the photon. There was a counter term for the fermion, IP slash del squared minus del M, right? And then there was a counter term for the vertex, which was proportional to delta 1. We said that ward identities non-perturbatively tell us that delta 1 is equal to delta 2. The full propagator for the photon takes the following form, right? This is D of Q, right? This form is fixed by Poincare invariance, and this is the gauge dependent part that we talked in detail about, right? The arc C gauge. So the form of these counterterms is precisely this calculation is precisely of the form that I just advocated. And you could, I'm not going to go back there, but you read off instantly gamma 2 and gamma 3. Gamma 2 is half M del M of delta 2. Gamma 3 is half M del M of delta 3. This is the renormalization of the 2-point function. For the 3-point function, there was the vertex, right? Psi bar psi AQ. This was the expression for it. You could calculate it. You could calculate the beta function is M del M of minus E del 1 plus E del 2 plus E over 2 del 3. You're going to go through these examples. I know that I haven't posted the homework yet, but I will do it tonight. Explicitly, delta 1 and delta 2 are going to take this form. Delta 3 is going to take this form. You've already seen it. You take the derivatives, and here they are. The gamma function, the gamma function and the beta function in QED. right? So this is the end of this lecture. Let me summarize it. I went through a lot of material, but actually, where did I start? I started by mm, repeating our story or reminding you guys of our story of Wilsonian RG as an integrating out a thin Euclidean momentum shell. We saw that RG was formulated in the Wilsonian language in 2 steps. Step 1, you integrate momentum shell, all effective changes, everything, all couplings are created, including even the coefficient of the standard kinetic term will change. We applied it in the second step. We did the scaling transformation and the field transformation. It's a wild transformation that brings the kinetic term back to its original form, so that the minus del mu half square, del mu phi squared is the fixed point of the RG, and then the rest of the couplings run. Everything that's allowed by symmetry is going to be generated, right? So this is renormalization group flow as described by Wilson. Operators are classified into irrelevant, relevant, and marginal. And from the point of view of the IR theory, so this B is the renormalization scale that you have to keep track of. Separation of scales tells you that everything is independent of the cutoff. We said that RG is irreversible, all of that. Oh, we discussed the situation with scalar field theory. In 4 and higher dimensions, scalar field theory, interacting scalar field theory cannot exist in the IR, right? Massive free fields is all we've got. In lower dimensions, it's possible. We saw that there is this trick of dimension 4 minus epsilon, famous epsilon expansion, which allows you to see within perturbation theory the existence of another fixed point for some critical coupling. But in general, it could be pretty wacky and it's complicated, right? And that's why we need a principle for strongly coupled QFTs, CFTs. Now, Callan Symanzik, to motivate Callan Symanzik equation, we talked about the running of the connected renormalized correlation functions. And the way we did this, we wrote down the connected correlator in terms of the bare correlator, right? Now the connected correlator will be calculated, the renormalized correlator will be calculated with counter terms as interactions that depends on M, couplings that depends on M, normalization of the field that depends on M, whereas the left-hand side, which is a bare calculation, has no M dependence. So the fact that there is no M dependence in the bare correlator tells you that you take MdM of the right-hand side, right? It should be 0. Beta functions were defined this way. We defined this gamma function, which is the wave function normalization, how it runs as a function of M. And we said that if renormalized perturbation theory, if you want to read off beta function, gamma functions, what you need to do is you have to extract the M dependent part of counter terms as you solve the renormalization conditions. You take the derivatives and you get your beta functions, right? So that was the story we told. There were a few more examples of 2-point function, 4-point function that I think I went through way too fast. I'll try to slow down next time. Any questions?
The beta function we get from Callan Symanzik and the ones we get from Wilson are actually the same.
Yeah, the definition was exactly the same, right? It was MdM of lambda of M.
So everybody had about like the relevant terms and general dimensions and distances. Does that change it like any of the dimensions is
Any of the dimensions are compact or not? Oh, as in like you're talking about space time. No. But as the short answer is in full generality is way too complicated. But in lower dimensions, where we do have a control over these type of questions, The answer is no. For example, take a two-dimensional CFD. A two-dimensional CFD will have an operated spectrum, so you're gonna have the spectrum of conformal dimensions, right? And if if there's an operator with dimension less than D or 2, you call that irrelevant operator. If it's equal to 2, we call that marginal. Anything above that is irrelevant, right? So the question is that what kind of CFDs have these like operators below that? And what the conformal dimension of the operator is independent of the background metric space-time, because you could take the cylinder, you could take flat space, compactify it using conformal map, bring it to a cylinder, your Hamiltonian has changed, but spectrum of the theory is not changed. In 2 dimensions, often the answer to these questions are easier in 2 dimensions because we have control over, and we have a deeper understanding of 2D conformal field theories.
What is the significance of that gamma function? Because beta function, I can understand it gives me the fixed point. But what about the gamma?
Anomalous dimensions. So remember the naive dimension counting thing? The naive dimension counting thing was telling you if those corrections due to loops are not present, you're so close to the fixed point, right? Then how does the under scaling, the field would transform up with the canonical with the scaling dimension, right? But due to quantum effects, that naive scaling dimension will change, will be shifted. The shift is actually captured by these gamma functions. It's anomalous dimensions. We'll hopefully I'll comment on that. I think RG is a long story, but I'm gonna pause now actually.